Let's do some examples of differentials in 2-space. So we'll just stick with the easiest examples. First, a quick review. A two-dimensional differential means we have two tangent vectors, and we're going to get the area of the parallelogram that they span, which is the length of their cross product. This is what we derived in the last video. So now we use it. This is a surface element, but if it's flat, it's called an area element, dA. All three examples are the equation z equals 0. We're just doing the xy plane. The only difference is the parameterization we use. So we'll start with the easiest. Substitute the equation into the coordinate system. Coordinate system's on the right-hand side. Location of the point xyz on the left. Rewrite it in vector form. Take our partials. There's our tangent vectors. Cross them, and we get our normal vector. Take the length of that normal vector. That is the area of the parallelogram that those vectors span. And fill it into our formula. Our dA, which is our surface differential. It's flat, so dA 1 dx dy. Look at the geometry of what we've done. We're in the xy plane, so we're looking top down in 3-space. I vary x while holding y fixed. I vary y while holding x fixed. Vary one parameter at a time. Now, increase my fixed parameter. I'm at x plus dx, and I vary y. Y plus dy, and I vary x. And there's my little surface element, dx by dy. Let's just look at the vectors now, and in 3-space. So we have our two tangent vectors. Put them in 3-space. Their cross product perpendicular. The k vector scaled by dx dy. We're going to be using all of this geometry later when we do surface integrals, so it's good to know it now. Let's redo the whole thing. We're looking at an area. That's just the xy plane. But now we use polar coordinates to parameterize. Right-hand side, our polar coordinate system, we substitute the equation in. Left-hand side, the location of the point xyz. Write it in vector form. And compute our tangent vectors. Just take our derivatives with respect to each parameter, varying one parameter, holding the other fixed. So it's a one-dimensional object, calc 1 derivatives. Compute their cross product. The length of the cross product is going to be the area of the parallelogram that they span. And we plug that into our differential. Looking at the geometry of what we just did, we're going to vary theta for a fixed r, get a little circular slice. Then we'll increase the radius by a little dr and do another circular slice. Theta is varying. Then we'll do the exact same thing for the other parameter. Fix the theta, vary r, increase theta by a little bit. Now the angle's a little wider. Vary r again, get another radial line. So the surface element is that little piece of shaded area, which we approximate by the differential, r dr d theta. Once again, let's look at the geometry just with the tangent vectors and in 3 space. So I have my tangent vector where I'm varying r. That's my variable, so it goes in the radial direction. I have my tangent vector in the theta direction. I put those vectors in 3 space. Both those are in the plane. Cross them, get the perpendicular vector. The k vector scaled by r dr d theta. We don't need to know the geometry now, but we will need to know this geometry later, so it's good to practice it. So when it comes, it's not a surprise. One last example. Same equation. So this time I'll do the standard thing. Since z is 0 in the parametric form, there's no reason to even write it. So I'll just write x and y. Now we have some other parameterization. So x is in terms of v and u, y is in terms of v and u, 2-parameter object. So that's a surface, the xy plane. Write it in vector form, and we'll compute our tangent vectors. I only have two components, but of course there's really 3, because it's -1i, 4j, 0k's. I'll need the 3 components when I do cross products. Cross them and compute the cross product. Take its length, 13. So dA, my 2 differential, my approximation to the surface area chunk, 13 du dv. Looking at my tangent vectors, the vector in the u direction is parallel to the -1,4 scaled back by du. The tangent vector in the v direction parallel to 1,3 scaled back by dv. Plot them in 3 space. They're both in the plane. I compute their cross product, which is perpendicular. Note the orientation, right-hand rule. RU cross RV would point down instead of up. Looking at the geometry of what we've just done, we look at our parametric form. So every point in the plane has an xy coordinate, which is given by a UV pair. So to find the grid lines, fix one of the parameters and vary the other. To see what it looks like, we'll either have to convert to equation form or use our calculator in the parametric plot. Whatever parameter you're varying, you'll call that t in the calculator. So we'll fix v and we'll vary u. Remember from the first week, pick one of the equations, solve for the parameter. That is now substituted in all the other equations. Removing the parameter. So it's a line of slope -4 with intercept 12v, some number. I know my tangent vector is -1, 4, so I know I'm heading in the -1, 4 direction in increasing u. U equals 0 is at the point, u equals 1, -1, 4 away. So for fixed v is the dark line, increase v by little dv, and I get my other grid line. Now I want to do the exact same thing for the other parameter. Fix u, vary v, solve for v in one of the equations, substitute v in all the other equations, removing v. And there's my equation form. A line of slope 3 with intercept 12u. Tangent vector is 1, 3, so I know I'm going in that 1, 3 direction, increasing v. V equals 0 is at the point, v equals 1, 1, 3 later. Increase u by du and get my other line. There's my little surface element, which I approximate using the differential. Here it's an exact approximation because everything's lines. And dA is 13 du dv.